The word contraction can mean shortening or developing force, with the result that concentric contraction, we need to distinguish between a contraction that's shortening and a contraction that isn't shortening. So we have a concentric contraction as a contraction that's resulting in getting shorter. An isometric contraction is a contraction where the muscle is getting neither longer nor shorter, it's staying constant length, isometric. And then eccentric contraction is when actually the muscle is getting lengthened while it's developing force. Isotonic contraction refers to a contraction of the muscle when the force against which it's contracting is constant, in contrast to isometric, where the length is constant. These two conditions are highlighted in blue because those are also the main testing and simplest testing configurations for muscle mechanics. They nicely test the force generation on the one hand and the shortening capacity on the other hand. The two most important experiments that we need to understand in muscle mechanics are the isometric experiment and the isotonic experiment. Some of the more interesting properties of muscle mechanics do not get revealed by those two experiments. So therefore, to understand some of them, we need to do some sort of transient or sudden loading. That gets a little more complicated. But before we worry about that, let's focus particularly on isometric and isotonic contractions, and we'll briefly give you some examples of what we mean by twitch and tetanus. Skeletal muscles, if you stimulate them to contract, they will generate a force and then they will relax, and the resulting waveform of force we would call a twitch. The process we would call a twitch, whether it was shortening or generating force. But if we held the muscle length constant, what we would measure is a change in force. The force would go up and then it would go down. Now, different types of muscles would twitch at very different speeds. Fast twitch muscles, like some of the small muscles in your eye, can generate force and relax very quickly. Slow twitch muscles, like some of the big muscles in your legs, for example, they generate force much more slowly and then they relax much more slowly. Cardiac muscle, by comparison, is even slower, so it's a very slow twitch muscle. Metabolically, these type of muscles are different too. The slow twitch muscles tend to be more in constant use. They tend to have higher overall metabolic requirements, and that's why this is the red muscle. Has more myoglobin and more hemoglobin, whereas the fast twitch muscle tends to be optimized to do its job quickly but doesn't have to do it as repetitively or as continuously, and so it has lower overall metabolic demands, but it tends to have different isoforms of myosin. So it has the isoforms of myosin that can hydrolyze ATP faster so that the cross bridges can cycle faster so that it can get its twitch over and done with faster. What determines the difference between the red slow twitch and the fast white twitch muscle is some combination of its myosin isoforms and its metabolic makeup as to whether it supports a more sustained slow work or a more occasional fast twitch. As you increase the frequency of stimulation, you reach a point where you can stimulate a muscle fiber to start to contract before it finished the last contraction. And that's because the electrical refractory period is much shorter than the twitch duration. So it's possible before this first twitch is finished to initiate a second twitch, which will actually result in a regeneration of force that's somewhat higher. And then you see the third twitch is even higher. And then if you go at an even faster rate, now you start to see an even slightly higher force development. And then if you go fast enough, you can actually stimulate the muscle to develop a sustained long contraction called a tetanic. So you don't only have to determine the function of the muscle by the twitch duration. By stimulating at a fast enough rate, you can produce this fused sustained contraction, which is the tetanic contraction, or tetanus. This diagram doesn't fully sort of illustrate the difference in the magnitude. The magnitude of typical tetanic contraction will be substantially bigger than the single twitch. If you take a skeletal muscle, and here we'll define 1 on this scale to be the force, or to be the length of the muscle at which there's no resting force when the muscle's at rest. If you stretch that muscle while it's at rest, they tend to be very soft, and so it's easy to stretch a skeletal muscle by 20, 30% or more. And you can see in this experiment, in frog sartorius muscle, it was actually possible to stretch it up past 50%. If you hold that muscle at any one of these lengths and tetanize it, stimulate it repeatedly to generate a force, you'll develop a much higher force. And in fact, the highest force you'll get will be very close to when the muscle is approximately at slack length. So this peak isn't exactly here at 1, but it's close. So you actually generate a lot of force when the muscle is slack. So the force on this scale, on the top scale here, is the total. The difference between the top scale and the bottom scale is the developed force due to the activation of the muscle. What you can see is that developed force, the difference between the resting curve and the total curve, falls off at lengths that are lower or higher than that length that's close to the slack length of the muscle. But nevertheless, it still operates over a fairly wide range of strains. So here we go from 0.5 to over 1.5. So over a wide range of lengths, the muscle can generate force, but it generates maximal force fairly close to the point at which it's roughly slack. And then if you stretch it, the force goes down, and if you shorten, the force goes down. And so this is a diagram that was published by Huxley and Joule that gave rise to the so-called sliding filament theory. And it's intended to explain that isometric length tension relation. So the difference between this graph and the previous one is that the total developed force has had the resting passive force subtracted. So now you get a peak, a plateau at the top, and you get a decline in developed force at different lengths. On the length scale now is striation spacing, is sarcomere length in micrometers, where the slack sarcomere length is approximately 2 micrometers or a little bit less. So you can see that around slack and for a little bit higher, as you stretch the muscle, you generate the maximum amount of contractile force. And that situation there is an interval between 2 and 3 on this scale. So here you see a cartoon of the sarcomere, and you can see what happens in that plateau between 2 and 3. The actin fully overlaps with all of the myosin heads in this cartoon, and the change in length as the muscle shortens a little bit from 2.25 microns down to 2 microns doesn't change that because there's an inner central portion of the thick filament where there are no cross bridges sticking out. If you go longer than 2.25 microns, you see that you start to now leave some of the cross bridges behind. And so in linear proportion to the length, the number of available cross bridges will go down, such that by the time you reach a length that's equal to the sum of the length of each of the actin filaments and the myosin filament, which is about 3.65 micrometers, there's no force left because there's no myofilament overlap available anymore. When you go the other direction and you shorten the muscle, what starts to happen initially between C and D here, between 4 and 5 on this scale, is that now the thin filaments start to interfere with each other a little bit, and that creates some resistance opposing the force. And then as you go further, now the filaments actually are starting to overlap with the cross bridges in the other direction. So these cross bridges here are actually working in the wrong way. And then at some point down here, when the muscle length is now approximately that of a single thick filament, somewhere between 1.6 and 1.0 microns, now you're actually starting to compress the thick filament and generate opposing forces that prevent any additional force from being generated. So this cartoon nicely explains the isometric length tension curve in terms of the overlap of thick and thin filament. And so that's called the sliding filament theory. The other type of experiment is an isotonic experiment or constant force experiment. And one way to think about a muscle holding on to a constant force is attach a weight to a muscle. Then the force is constant regardless of whether the muscle shortens or gets longer. Normally the way the isotonic experiment is done is that you first of all start to generate force isometrically by tetanizing the muscle. So this is time on this scale here. The length is being held constant here. And as you tetanize the muscle, the force goes up. At some point, the force gets high enough where it pulls a catch, and then the force goes from being constant length to constant force. And that constant force is lower than the force that it had just reached. So you have a muscle contract, and then you generate a certain amount of force. You switch over to a lower force, and you switch over from constant length to constant force. So what happens when that happens? The muscle shortens. So the force is lower, which means that the amount of force opposing the muscle contraction to keep the muscle in the same length is less, so suddenly the muscle shortens. So the next question is, if you drop that force a little bit versus a lot, what would the difference in the shortening be? So you're trying to pull open a door that's very stiff, and suddenly it releases, and there's no load at all. Versus you're trying to pull on a door that's very stiff, and suddenly it releases a little bit, but it's still really got a lot of friction, and so there's still some force. It's just low enough that you can start to open it. So what's the difference? The rate of shortening. If the force went all the way to 0 versus if the force only dropped a little bit, which would have the higher rate of shortening? If it dropped all the way to 0, then you'd shorten the fastest. If it dropped just a little bit, you wouldn't shorten so fast. If it didn't drop at all, you wouldn't shorten. So that's the basis of a relationship that I'll show you in a minute called the force-velocity relationship. But this is how you measure it. You tetanize the muscle at constant length until you reach maximal force, and then you drop the weight isotonically to a new lower load. What happens is it shortens, and it will shorten down to some new length. Out here, it's now back on the isometric length tension curve at a lower point. But in the meantime, it shortened at first fast and then slower. And then if you can find a point on this curve where the rate of shortening is fairly steady, Usually just after some initial transient, you measure the rate of shortening. You plot that against this force. The lower this force, the higher that rate of shortening. So this is the curve you get, where this is the force, and this is the rate of shortening, which is confusingly called velocity. Physiologists and biochemists like to use velocity for the oddest terms, and rate of shortening is really a rate of length change, not a rate of distance change. This is the velocity. It's a velocity of shortening, so it's a negative strain rate. And the force here is normalized by the isometric force, T0, because if you started off at isometric force, T0, and you didn't change the force at all, what would the shortening velocity be? 0 would remain isometric, so there'd be no change in length. So when the shortening velocity is 0, the force is isometric, so T is equal to T0, or T over T0 is 1. But when the force that you go to is lower, you can see that it starts to speed up. It's maximal when the force is 0. So if you release all the force, then the muscle will shorten fastest, and that rate of shortening is called Vmax. So again, if you normalize the x-axis of the plot by Vmax, you'll get a curve that goes from 0, 1 to 1, 0 in an inverse way. And that's called the force velocity curve, or Hill's curve. Now you could say, well, what happens if instead of shortening you were lengthening? And so there is a lengthening part of the curve as well. But the greatest emphasis is on the shortening, because remember I said that the basic thing the muscle is designed to do is to shorten and or develop force. The rate of shortening, the so-called shortening velocity, is the way that we measure the shortening ability of the muscle. And it follows a curve like this, which Hill found looks like a hyperbola, and actually is fit quite well to a hyperbola. And he thought that there was a theoretical reason why it should be a hyperbola. It turned out there wasn't. Nevertheless, this curve does have thermodynamic significance, because if you take the product of force times rate of change of length, force times velocity, what do you get? Force times rate of change of length is power. If you multiply these corresponding points on this curve, or more precisely if you integrate under this curve, you'll get a curve like this. So at one end it's 0 because you have a 0 for V. The other end it's 0 because you have a 0 for T. So you have no power at the isometric or maximum shortening cases. But in between, you get a rising power. So somewhere in between isometric and maximum shortening velocity, you get the maximal power output of the muscle. Hill, as I mentioned, observed that this curve had a hyperbolic shape, and here on this version of the curve, this value B over Vmax and this value minus alpha over T0, those are the asymptotes of that hyperbola. And so this is the equation that Hill wrote, that T plus A times V plus B equals T times T0 plus A. So assuming we know the isometric tension, this is really a two-parameter fit. Or I find it more useful to non-dimensionalize it just the way we did in that graph. So that means that you can write V over Vmax as 1 minus T over T0 over 1 plus C times T over T0, which also can be rearranged to be T over T0 as 1 minus V over Vmax plus over 1 plus C times V over Vmax. In other words, the three parameters of the Hill hyperbolic relationship between force and velocity, or tension and rate of shortening, are T0, the isometric tension, Vmax, the maximal shortening velocity, and C, which just determines how nonlinear that hyperbola is. What would the shape look like if C was 0? Just be a straight line. So, but in fact, it's a little curved, and so C has some value typically between 1 and 4. Technically, what I've shown you so far on the force-velocity relation is just for concentric contractions. You can also measure a force-velocity relation for negative shortening velocity, namely lengthening rates. And as you can imagine, if a muscle is developing isometric force and then you try and stretch it, the force is going to go up. And it goes up in a somewhat nonlinear way like this. And so there is an eccentric part to the force-velocity relation. What happens is that you end up getting very high stresses, and so eccentric exercise tends to produce muscle damage. And muscle damage is not such a bad thing if it's not too severe, because muscle has satellite cells that constantly rebuild muscle. And certain muscle diseases like muscular dystrophy are thought to be because of an inadequacy of these cells to regenerate the muscle. The other thing that Hill is famous for is the so-called Hill three-element model. I'm not going to go through this model in detail, basically because it's wrong. It's widely used, though, because it's useful. And I'll tell you what the basic ideas are, but then I'll also tell you what the limitations are. So Hill postulated that you could model muscle by considering three elements, much like we did in viscoelasticity. where two of those elements were springs, and one of them was the contractile element. This is the thing that makes muscle different. So the first thing he assumed was that the resting properties of the muscle, so that resting length tension curve, was entirely due to this parallel elastic element. So that assumes that this behavior is elastic, not viscoelastic, doesn't have to be linear. So that actually automatically tells you something about the contractile element. The tension in the contractile element when the muscle is not contracting, when it's not activated. It's zero, because if it wasn't zero, then the overall length tension property of the model would not equal the resting length tension property, which we just said that it did. Just from looking at this diagram, what can you say about the relationship between the passive force and the total force? Don't overlook the obvious here. They're added, they're in parallel. So the total force is equal to the resting force plus the force in the contractile element. What we already did, which was to look at the total force and the passive force and then call the difference the active contractile force, was Hill's assumption that you can add them together. Put another way, when you do that, if you define the developed force to be the total force minus the passive, you're assuming that the contractile element is structurally in parallel with the elements that are responsible for the passive behavior, which may not be completely true, right? It may be more complicated, but that's the widespread assumption, and that isn't the part of the Hill model that I have a problem with. The second assumption, and you could think of this as two assumptions by Hill, is that the properties of this contractile element are completely defined by two measurements that we now know about. One is the isometric length tension relation, and the other is the isotonic force velocity relation. So you can think of the isometric length tension relation as a special kind of spring, right, where the tension depends on the length according to some non-monotonic property. And then you can think of the force-velocity relation as sort of being some special kind of dashpot, some special kind of syringe, where the tension depends on the rate of change of length inversely. So it's a little bit like a viscoelastic model in concept, but in detail you're saying that the two things you need to define the contractile properties completely are the isometric length tension curve and the isotonic force-velocity relation. And as long as you have them, and you put them together in this model, then you can predict anything else. And it's not entirely true. But it's not such a bad assumption either. They're the two single most important things. If you only had two properties of the muscle you wanted to include, those would be the two to put in. They're just not enough to be completely right. Now, the third one gets a little bit harder to justify, but this is the series elastic element. Hill found that these assumptions weren't quite enough to explain experimental observations. And there's various reasons for this, and some of it is no more than straightforward experimental artifact. For example, if I take a skeletal muscle and I grab onto the two tendons and I hold the length between them fixed, and I stimulate the muscle, what actually happens to the sarcomeres in that muscle? Do they stay the same length? They get shorter. So why, if I'm holding the length of the muscle fixed, do the sarcomeres get a little bit shorter? The tendons are getting stretched a little bit. So when you generate the force in the muscle actually shortens a little bit and stretches the ends of the muscle, either the part of the muscle where there's no muscle cells at all, like the tendons, or maybe the part of the muscle that's more tapered down, where there's less muscle cells. So since the force development is high in the middle, then that can actually pull on the elastic structures at the end to cause shortening. So part of Hill's need for a series elastic element was because he didn't recognize that this was happening in experiments. And actually, if you were to describe the Hill model that way, what you'd probably prefer to do is take the series element and put it out here and series there. Series elasticity exists in real experiments, but it's not sort of an intrinsic property of the muscle. Another is because when you did these type of transient experiments, like this one, you get this somewhat complicated transient behavior that couldn't be explained simply by the force-velocity relation and the length tension curve. Something else was going on, and Hill assumed that what was happening is that the length was changing due to series elastance, and that would explain this. So what are the limitations? First one is that the series elastic element could actually have been in series with the other two that were in parallel, or it could be, as I showed you, in series just with the contractile element. None of what Hill said helps you discriminate those two things. Mathematically, they'll give rise to the same model, but structurally they'll mean different things, and the parameters of the model will be different. And so there's one basic problem with Hill's model is it's imprecise. It's not unique. The Hill model is only valid for steady shortening or isometric conditions. It's trying to predict what happens in between those conditions, but it doesn't actually work. It works okay, but it doesn't work completely properly. Another thing we need to take into account is the fact that when you tetanize a muscle or when you activate a muscle to contract, it doesn't stay steadily shortening or steadily developing force. The force goes up and then goes down. According to the demands, it might go up and down as you walk. None of that's included in this model. So you'd have to superimpose at a minimum some additional idea of the amount of activation of the muscle. Like the transient responses that people have now been able to observe by doing fast step changes are not consistent with the Hill model. And most importantly, as I alluded to, the series elasticity is not actually seen. They're either properties of the tendons or things that are in series with the muscle, or they're actually inside the muscle. In other words, there is actually some series elasticity of a kind, but it's not in series with the contractile element. It's actually in the contractile element. So here's one of the types of experiment that the Hill model does not explain. This is an experiment where the muscle is held isometric and then it's shortened very rapidly in an interval of 1 millisecond, but also by not very much, only by less than 1%. So you have your muscle tetanized, developing constant force, and then you just make a very small shortening. The force velocity curve might say that during that very short interval, the force would go down. But it then should almost instantaneously come right back up to the isometric value. That would almost be exactly the same as this, because the difference in length here is like less than 1%. But actually you can see what happens is the force does instantaneously go down, and it goes down faster than you would predict from this force-velocity relation. It goes down instantaneously, and it goes down a lot. This was only less than 1%, yet the force transiently drops almost all the way to zero. And then as it redevelops force over the next 50 milliseconds or so, it does so with a rather complicated but characteristic time course, which turns out to have to do with the time course of the cross-bridge cycle. Because this is how long it takes for the cross-bridges to attach and go through their cycles and develop force. Okay. So you can see they attach here, and then they develop some force, and then they go through the cycle and they develop more. What about this very, very sudden drop in force? How can that be explained? Well, if you plot that sudden drop, so this force, this new force here is labeled T1. And so if you plot that as a ratio of T0 against the size of the shortening step, what you see is you only have to get to a shortening step of minus 6 nanometers per half sarcomere. 1 sarcomere is about 2 microns, so half a sarcomere is 1 micron, so 1 nanometer is 0.1%, so 6 nanometers is 0.6%. So you only have to shorten that muscle by 0.6% for that tension to go all the way to zero. Very, very small. And furthermore, how much the shape of that curve is essentially a straight line. If you go to a different point on the length tension curve where the T0 is lower, interestingly, it has the same intercept, but the slope is proportionately lower. So if the isometric tension is 40% of the value, the slope will be 40% of the value. So this stiffness is somehow determined by the same thing that determines the isometric tension. So what determines the isometric tension? What determines how much force this muscle can generate? Think of the sliding filament theory. The number of available cross bridges determines the isometric tension. If there's none, it's zero. If it's maximal, it's maximal. That's the difference between this curve and this curve, is that this one's 0.5 and this one's 1, roughly. So there's roughly half the number of available cross bridges, or a little less, 40%. And consequently, the slope of this curve, when you do this very, very rapid, quick, small shortening, is proportionately lower. So this curve suggests there's some elastic property, and that elastic property is proportional to the number of attached cross bridges. So what's the simple interpretation of what's going on here? And the diagram kind of gives it away. Interpretation is that each cross bridge is a spring. It's a relatively stiff spring, but if you shorten those cross bridges by about 0.6%, all the force will go out of them because you just released this spring. But they're still going through their cross bridge cycle, so they'll power back up in the course of the next 10, 20, 30, 50 milliseconds. And so this result here really proves that the cross bridges themselves are elastic. Part of the series elasticity is just an artifact of tendons or attachment at the end of the muscle. Part of it is actually a real property of the cross bridges themselves, which are the contractile element. Of course, Hill in 1938 knew nothing about cross bridges. Didn't even know about sarcomeres. So he was just postulating the existence of some magic force generators. Well, those magic force generators do have elastic property, but it's inside them. It's not in series with them. And so that gave rise to what's called the Huxley and Simmons model, that is a variation of the original Huxley's 1957 cross-bridge model, where Huxley had allowed that the thick filament could form cross bridges with the thin filament in a kinetic way, in a way that would go on and off in a cycle. And so the cross-bridge cycle is really due to Huxley's theory. And what Huxley and Simmons did is extend that theory by allowing the cross-bridge to be an elastic spring that would occupy these different states. And as it went through those states, it would stretch that spring. As a result, the Hill model can't explain this transient experiment. And the Huxley model that considers the cross-bridge as a force generator that has some elasticity can. And here's just a little cartoon of the Titan. And then I'll leave you to review the summary points before we go on to heart muscle next time.